Have you ever wondered why functions are so critical in information technology? Well, they're the building blocks of code, breaking down complex problems into manageable tasks. Functions, or as some may call them, procedures or subroutines, are like the gears in a well-oiled machine. They promote a concept known as modular programming. This process involves dividing a large program into smaller, self-contained modules, with each function focusing on a specific task. Not only does this make the code more organized, but it also enhances code reusability. Imagine writing a piece of code once and being able to call upon it multiple times from different parts of your program. Sounds efficient, right? That's the power of functions. They encapsulate implementation details, allowing users to focus solely on their purpose and usage. So, without functions, our code would be much less efficient and more difficult to maintain. But what exactly are these functions? In the simplest terms, functions are blocks of code that perform a specific task. They are the backbone of any programming language, also known as procedures or subroutines. These fundamental building blocks of code can be likened to a chef's recipe, detailing the steps to whip up a culinary delight. Just like a recipe, a function has a name, ingredients, which we call parameters, and a set of instructions to carry out its task. Functions play a crucial role in breaking down complex problems into smaller, manageable pieces. Imagine trying to build a car from scratch without dividing the work into assembling the engine, the chassis, the interiors, and so on. Functions help us do just that in the world of programming, making our code more organized, efficient, and reusable. They are the unsung heroes that keep the digital world ticking smoothly. Now that we understand the basics, let's delve into the key aspects of functions. One of the major benefits of functions is their support for modular programming. Imagine a large, complex piece of software as a jigsaw puzzle. Trying to assemble it all at once would be overwhelming, wouldn't it? That's where modular programming comes in. It allows us to break down that daunting puzzle into smaller, manageable pieces, each representing a specific task or functionality. These pieces are our functions, our self-contained modules of code. Each function has a specific role. It's like a specialist in a team, focusing on what it does best. This way, we can build complex software from simpler building blocks, making the development process more manageable and the code easier to understand. But the power of functions doesn't stop at modularization. They also champion the cause of code reusability. Imagine having to write the same lines of code over and over again in different parts of your program. Sounds tedious, doesn't it? But with functions, we can avoid this redundancy. Once a function is defined, it can be summoned or called from any part of the program as many times as needed. Even better, the same function can be used in totally different programs. This way, we not only save time and effort but also maintain consistency across our code. Moreover, reusing code reduces the potential for errors. When a function is tested and verified, we can be confident that it will perform its task correctly every time it's called. So by reusing functions, we're also enhancing the reliability of our software. But what happens when we need to modify our function? Fear not. Since a function is a self-contained module, changes made within it won't affect the rest of the program. This isolation makes debugging and updating our code much easier. So, functions help us structure our code efficiently and avoid repetition. But that's not all. Stay tuned as we explore more about the magic of functions in the upcoming scenes. Scene script. Functions also provide a level of abstraction and allow for parameter passing. Let's dive into abstraction first. Imagine you're driving a car. You don't need to know the intricate details of how the engine works to be able to drive. You just need to know how to operate the controls. This is a form of abstraction. Similarly, in the world of programming, functions encapsulate certain complexities, allowing you to focus on the bigger picture. You don't need to understand all the inner workings of a function to use it. You just need to know what it does and how to call it. This is the power of abstraction that functions provide. Now, let's move on to parameter passing. Think of parameters as the ingredients in a recipe. Just as a recipe can be customized by changing the ingredients, a function's behavior can be modified by changing its parameters. When you call a function, you can pass different values as parameters, and these values will influence the function's behavior. This is known as parameter passing. Let's consider an example. We have a function that calculates the area of a rectangle. The parameters for this function would be the length and the breadth of the rectangle. By passing different values for these parameters, we can calculate the area of different rectangles. So, if we want to find the area of a rectangle with a length of 5 units and a breadth of 3 units, we would pass these values as parameters when calling the function. In this way, abstraction helps to hide the complexity of a function, while parameter passing allows for customization of the function's behavior. These features make functions not only versatile but also user-friendly. They enable programmers to write more efficient and manageable code, thereby enhancing productivity and reducing errors. But wait, there's more to functions than just abstraction and parameter passing. These features make functions versatile and user-friendly. But how do functions communicate with the rest of the program? Functions communicate with the rest of the program through return values and have their own scope. This is a fundamental concept in understanding how functions operate within a program. But what does this mean exactly? Let's start with return values. When a function completes its task, it can return a result or an output back to the part of the program that called it. This is what we call a return value. It's like the function saying, "Hey, I finished the job you asked me to do. Here's the result." For example, a function that adds 2 numbers together would return the sum of those numbers. This return value can then be used elsewhere in the program, perhaps to feed into another function or to be printed out for the user to see. Now let's talk about scope. Scope in the context of functions refers to the visibility or accessibility of variables. Each function has its own scope, meaning the variables defined within a function are local to that function. They are born when the function is called, and they cease to exist when the function finishes its execution. This is known as the lifetime of a variable. Imagine a function as a little world of its own. The variables within this world are only known and recognized within its boundaries. If you try to access a variable outside of the function where it was defined, the program will simply say, "I don't know what you're talking about." This concept of scope is crucial as it ensures that variables within a function don't interfere with variables of the same name elsewhere in the program. It keeps our code tidy, organized, and free from conflicts. So functions not only perform specific tasks, but they also manage their own variables and communicate results back to the rest of the program. They are like little self-contained units of code, each with its own job and its own environment. Functions, it seems, lead quite independent lives within a program. But can they call upon themselves? That's a question for our next scene. Stay tuned. Functions can indeed call upon themselves through a process called recursion. This is akin to a Russian nesting doll scenario, where each function call opens up another layer of the same function. Recursion is a powerful tool in programming. It allows us to solve complex problems that can be divided into simpler instances of the same problem, like traversing a tree structure or sorting a list of items. Remember though, recursion should be used judiciously as it can lead to heavy memory usage if not properly managed. Next, we have library functions. These are pre-packaged solutions provided by programming languages and frameworks. Library functions are akin to a well-stocked toolbox, brimming with tools that are ready for use. They cover a wide range of functionalities, from mathematical operations to file handling, from network communication to graphical user interface creation. By using these ready-made functions, developers can save time and focus on the unique aspects of their code rather than reinventing the wheel. Finally, let's talk about event handling. In the world of event-driven programming, functions often serve as event handlers. Picture this. You're designing a graphical user interface and you want something to happen when a button is clicked. This something is defined in a function, and this function is set to respond to the button click event. Functions used in this way allow us to create dynamic and interactive applications. Functions, whether they're recursing, hailing from a library, or handling events, are key to creating effective and efficient code. They help us break down complex tasks into manageable pieces, reuse code to save time and effort, encapsulate details to maintain a clean interface, and respond to user interactions to create dynamic applications. As we can see, functions are versatile tools that make our coding lives much easier and our programs much more efficient.